Our next speaker today comes to us from Robert Bosch. Give a warm round of applause for Mr. Michael Bolle.
Yes, good morning. And a very warm thank you to Ranga, who really made up the universe of artificial intelligence. And I will now talk about the Bosch perspective on artificial intelligence and our approach to AI, always under our motto, which is invented for life. So Ranga mentioned this one already. So we have seen in the past 2 decades really big successes of machine learning and artificial intelligence. So it started 1997, when first time a computer program got success against a leading human player. So this was the first instance where really machines were, in a certain perspective, better than human beings. In 2011, the Watson program showed that also in interaction games, Jeopardy was this game, computers are able to outperform human beings. And in 2018, we have seen question and answer systems, and the video we have just seen from Google also underlined this, where in question and answer situations, machines could perform better than humans. All these examples are in narrow fields, where the set of rules which describes the situation are really finite. And in the bottom of this slide, you see an example which we typically call an open world problem, where, for example, a car drives autonomously in the streets or in urban areas. And the first step in this direction, which is much more complicated than the situation in games, has been done in 2005 by University of Stanford and Sebastian Thrun, and actually a Bosch team in the US was part of this exercise. And 2016, we had the next step of evolution in the gaming, where Alphago defeated the world best Go player. And this was remarkable because in the years before, the assumption was that the complexity of Go is so high that machines will not outperform humans. So this shows that in the last 2 decades there has been a lot of progress. But I would like to mention one point. The term artificial intelligence was invented and brought up 1956, the famous Dartmouth conference, where Marvin Minsky, Claude Shannon, and others, inspired by the invention of semiconductors and computer architectures, were of the opinion that we could tackle the field of artificial intelligence in a short-term future. So in this conference, people said, in the term of a few months, the best brains and the best heads in the world should be able to solve important challenges of artificial intelligence. History has shown that this has not been possible, and the last 2 decades has shown that we are improving now, but there are still big challenges to be solved, and I will later come to those challenges. Now, today, and Ranga showed this universe, everybody is talking about artificial intelligence. And on the left-hand side of this slide, we show, let's say, the fields of artificial intelligence, which have been, in the early days, very much focused on symbolic AI, so try to cover the logic of human intelligence with symbolic and logic architectures. We had the field of knowledge representation. We had related fields like robotics and computer vision. And we have one field which is called machine learning, which is most prominently dealing with data. And all the results which we have seen so far, also on the previous slide, are due to the fact that the improvements in machine learning have been so overwhelming. And in the machine learning, we have basically three categories of algorithms we are talking about. It's probabilistic inference, that's generating models out of data and use them to predict behavior in the real world. We have reinforcement learning, which is dealing with the interaction of agents, so for example, autonomous cars, with the environment. And we have deep learning, which Ranga also explained, which is dealing with neural nets. And the question is, what changed in the last 2 decades so that we see this improvements and this much greater performance of machine learning? And if we categorize the fields where we have seen these successes, it's in the field of face recognition, it's natural language processing, language interaction. This was the example shown by Ranga before. Perception, so perception of the environment, for example, in autonomous cars. Games, the famous examples of DeepMind in Atari games. And the object recognition, so detecting objects out of images. These were the main success factors or success examples of machine learning. And the key enablers for this are shown bottom left of this slide. So first of all, increased computer power. So semiconductors and semiconductor chips have become so powerful that the complex neural nets, which are shown on the top of this slide here, can be executed in real time and can be trained accordingly. The second very important point is the availability of large public data sets. And this started with the ImageNet database, where we see examples on the right-hand side, where Stanford University started to collect images and annotate those images with content. So, for example, on the right-hand side, you see a dead mask and you see a sea star, and humans labeled and noted the content of those pictures. And 7 million of those pictures have been collected, and these pictures have been used to train the neural nets. And these databases have been made public, so the research community could work on this data set and could use this data freely. Algorithm advancement, so the basic concept of a neural net has been developed very early on. These algorithms and architectures have been worked upon. Convolutional neural nets have been introduced as a new mechanism. So also there we had seen advancements. And the last point is the whole field of connectivity, connectivity of sensors to the Internet of Things, connectivity of computers itself, and connectivity between the researchers. So these were, in our understanding, the main factors why the performance of machine learning so much increased over time. And on the right-hand side, bottom of this slide, you see a picture of recognition error rates in this ImageNet example. So the task here is that the computer gets a picture and has to determine what is the content of the picture. So on the left-hand side, he sees a sea star, and on the right-hand side, he sees a dead mask. And in this chart, you see, based on classical algorithms, so until 2010, the performance stagnated to around about 27–28% accuracy. And with the introduction of machine learning and large annotated data sets, the performance improved over time significantly. And between 2014 and 2015, this network outperformed human performance. And Ranga mentioned this as well. But we have to understand that this performance and view on performance is a very narrow field of application. Now, what are the challenges? So first of all, and I've mentioned this, neural nets, deep neural nets, machine learning heavily relies on data. And this data has to be prepared and accordingly labeled. And this creates a huge scaling issue for machine learning and artificial intelligence. In this slide, I give you an example. On the left-hand side, you see a neural net. And you can see some elements of this. On the left-hand side, you have the input layer, where basically the data is inputted into the network. In this example here, it's an image. Image consists of pixels, and each of these pixels is fed into this network. So each of these nodes, which you can see here, is basically a pixel. So you can imagine if you have a full-size image, you have a huge amount of pixels and nodes which have to be processed in parallel. The second element of this network is this layered structure. And between each layers, you have a full connection. So you have edges between these nodes, and each edge contains one multiplication of the input signal of the input node with a parameter, and an output value is created. And the nodes, this is exactly what Ranga has explained before, is this main element of a neuron, where those results are summed up and then fed into nonlinearity. That's the basis of a neural net and a deep neural net. And in order to give you some figures about complexity, so on the right-hand side, you see a famous application which we use in the automotive space. We call it semantic segmentation. And the basic idea here is you have a front camera with an input sequence of frames. And now for each and every pixel of this input signal, the net detects what is in it. So is it a street? Is it a car? Is it a passenger? And in order to achieve this kind of performance here, you need very deep networks. So to give you an idea, it's about 120 to 180 layers which are used here. And if you do the whole math, then you clearly understand that the number of parameters which are in this deep neural networks is several million. So you have to optimize a network with 30 million parameters, for example. And in order to do this, you can imagine that you need a huge set of data which is annotated and which is labeled in order to optimize 30 million parameters. And currently, we are collecting these video sequences with petabytes of sequences. And each of the sequences has to be labeled by human beings. And this is an increasing cost factor, which is limiting the applicability of the whole system here. And due to this, a whole industry has evolved, which deals with automatically labeling, or not automatically, manually labeling data. The first examples was the Mechanical Turk of Amazon, and then other systems have evolved, where basically this task of labeling data is fed into a network of micro workers. These people then judge on the data and say this is, for example, a dead mask, or this is, in this example I have shown, this is a passenger, and so on. And fed this back in the database. And today, more than 1 million people are currently working in this field and space of labeling data for machine learning. And obviously, this does not scale, so we have to think about what can we do in order to reduce the manual interaction on the data side. And the point I would like to make on this slide here is that basically we have two approaches to do this. Everything we have seen so far in machine learning is what we call supervised learning. So you have data, and this data is annotated by human beings, and this is used in order to optimize the deep neural nets. This example is the handwritten digit classification, which is a famous application where you use in supervised learning, you have to use 60,000 images in order to train the network. And each of this image has to be labeled by a human being in order to say what is in. And the holy grail of machine learning is shown on the right-hand side. This is unsupervised learning. And that's the idea, to generate the knowledge and the network without human labeling or with drastically reduced human labeling. And the basic approach we can take here is to introduce knowledge into the system. So in this example of handwritten digit classification, it has been shown that you can reduce the number of labeled images needed to 0. And how do you do this? You introduce knowledge about the problem itself. And in this case here, we have the case of a structured data. So basically, you have 10 digits. You know you have 10 digits. And that each of the image which you fed into the system exactly shows one of those digits. And this is enough in order to train the network unsupervised and generate the automatic recognition. So this is a very promising approach. It's in the early stage of research to do it in more complex situation, like I've shown. Now, another approach in introducing knowledge is shown here. So in this example, the problem is to estimate the pose of human beings. So on the left side, you see a sports application where people are doing sports, and the system automatically has to generate the pose of the person. So in which situation from a body perspective is he? And in order to do this unsupervised, you need to label all these images, which is a very tedious task. And now the approach in order to reduce this is to use the knowledge, to introduce knowledge here about the skeleton of the human being. So we know how the skeleton is composed, and introduce this as boundary condition in the learning scheme, and drastically reduce the amount of data which is needed in order to train the system. On the right-hand side, you see an application. Oh, video is not showing. Here we have an application of autonomous driving, where the system detects a person and now has to detect what is this person doing next. And one example or one application of this is doing this pose estimation and use a prediction into pose in order to understand what is this person doing next. This is an active research field we currently have. Now the next challenge, so this was about data, and the concern here is that this labeling of data is a huge cost factor. It's increasing, and we have to find unsupervised machine learning approaches in order to tackle this. The next challenge is to make artificial intelligence safe, robust, and secure. And this relates to the point we have seen before, and also mentioned by Ranga, that we say the neural nets and the machine learning algorithms rely on data, and they learn out of data. And in this respect, the attack surface for this system is no more a hacker who goes into the algorithm and do something evil. The attack surface now is the data itself, which makes it very scary. And we see here some example how this works out. And on the top of this slide, you see an image recognition, where the system has learned how to recognize people. So here it's Reese Witherspoon, and the network correctly categorize this image as Reese Witherspoon. In automotive, you have signs which are used in traffic, and on the left-hand side you see an stop sign with a graffiti, and this is correctly recognized as a stop sign. So on the top of this slide, everything is OK. Now, we can change or perturb the data itself. This is shown on the bottom. So one famous example is using these glasses. So we impose a synthetic glass on the image of Reese Witherspoon. So this is then fed into the neural net, and the result of the classification is Russell Crowe. And you can do other attacks as well. You can do small perturbations on the input data, which leads to wrong classifications, up to the fact that you change, for example, only one pixel and you get a wrong classification. So the networks are not robust. In our automotive application, this has been shown on the bottom right. So you have a stop sign, and this is an example of a physical attack. So this can be done in reality. You do stickers on the stop sign, and the stop sign is wrongly detected as a speed limiter. Now, we have done research in this field as well, and have asked ourselves, can this be done on sequences as well? And here on the top of this image, you see a semantic segmentation on a video sequence trained, and the result is shown. So you see top right, you see people moving over street, and you have some trees in the background, also some other cars in blue. Now on the top, you see a disturbed sequence with one overlay which you can hardly see. So if you go very closely to the image, you see that we have overimposed a static pattern on this video. And on the right-hand side, you see that the system completely falsely detects the situation itself. So this just illustrates that there is a huge attack surface on the data itself, and we are working on methods, algorithms to make the networks more robust, or alternatively to detect when such attacks happen in reality. Now, another approach to safety is in the field of autonomous driving, and autonomous driving is one of we call it the killer application of artificial intelligence. That's the question: how do we deal with rare situations? What do I have to do in order to start the video? Thank you. So on the left-hand side, you see a situation where a children is crossing a street, which is potentially a dangerous situation, and you can imagine other very dangerous situations which are difficult and which we do not like to have in the traffic situation. On the other hand, in order to make our networks to deal with this situation, you have to have those situations in the data set itself. So this creates a problem, because these situations very rarely occur, and you have to have solutions in order to do this. And on the right-hand side, and maybe you can start this video as well, our approach in this respect is to go for simulations. So we simulate the whole world and use this simulated data as input data in order to train the networks, which is much more safe, which is much more cost-effective, and you can really have a focus on these rare events. Now, the question is, what do we do? How is our approach? And what I have shown to you are really challenges, which are research challenges, which have to be tackled, and therefore we have started the Bosch Center for Artificial Intelligence in 2017 with a global footprint. So we are active in the US, in Germany, and also in India. We invest 300 million euro in the next 4 years. And one important thing, and this relates also to the enabling point which I've shown about availability of data sets and close cooperation between the people. We are very much engaging in academic partnerships. So we are actively driving the Cyber Valley in Tübingen. We have a cooperation with Max Welling in Amsterdam and the CMU in Pittsburgh. And today, we have already 80 active projects up and running with the various business units and fields in Bosch. And the research fields are detected in such a way that they really tackle the points which I've mentioned before. So make AI safe, robust, and explainable. And on the last slide, I would like to summarize the challenge which we have. So on the first hand, explain deep learning. So understand the mechanisms of deep learning and make the networks more robust. The second point is think about generalization properties. So I've explained that these networks are trained on test data, but these networks are applied in reality. And this is what is typically called generalization. And the basic mechanisms of generalization are not fully understood. And in order to give guarantees, and as a technology and industry company, you have to give guarantees for your products, you need to understand and to bound the generalization properties. We will look more in the structured knowledge space, so reducing the amount of training data which is needed and inject knowledge. And the last point I would like to mention, also mentioned by Ranga before, we simultaneously have to work on the ethics side of machine learning and artificial intelligence. We are doing this actively, so we are not only doing research in technical field, we are also doing this in the ethical field. And one important question is to derive, for example, properties of data sets, and detect, for example, whether there is a certain bias in the data which we have to understand early upon. So these are the research challenges we address. AI is a very promising field for us. We are convinced that it will be a disruptive technology. But on the other hand, looking at the challenges which I've outlined, we feel AI is rather at the beginning. It's still evolving, and we need some fundamental results, and Bosch will be part of a partnership generating those results. Thank you very much.